summarizing Einstein's theory, space-time is warped by matter energy. Within that space-time, free particles move in such a way that their world line is a geodesic of that space-time. So you don't say it moves along the geodesic, but take the space-time that results from the matter energy curving the space-time, figure out what is the geodesic, again, given that initial condition of how it starts off moving. You could then plot the rest of its world line. Given that world line, you can find out what its trajectory was in space. Okay? So you have this feeling that, you know what? Maybe I can formulate some kind of a law that particles in free fall move along geodesics of the spacetime, or their world lines are geodesics of the spacetime. Okay? If you look at the surface of, let's say, a sphere, all right, you know that the geodesics, the shortest or straightest lines are great circles, right? If you draw this great circle and you draw this great circle, at first they're parallel in the ordinary sense, okay? It's just like on Earth, if you took this line and this line, right, along this floor, all right, in theory, if you continue straight along these lines, they should never meet. But of course, we know that if you start like this, because the Earth is curved, they're going to meet. If you start with any two lines at any pole, right, even if they're diverging, eventually they'll converge. And then on the other side, they'll diverge again and converge again on the other side. Instead of saying we are in the gravitational force field of the Earth, we say the Earth creates a curved space-time. So what happens is that geodesics, which are initially seemingly parallel to each other, diverge and converge. So therefore, a theory of tidal forces is really a theory of curvature. Two world lines of particles in free fall, which in theory ought to be in inertial motion along straight lines, converge or diverge, which is exactly the same thing as saying there is a gravitational force and there is a tidal force, except that by recognizing the fact that the gravitational force disappears, we rule out, we just don't talk anymore about a gravitational force because there is no such thing. It's exactly the same as inertial forces that arise or in non-inertial motion. If you're rotating, if you're in a car that's turning, you feel these forces pulling you and pushing you and so on. You might say that, oh, well, there's some galactic effects causing you to be pulled this way, and there's some kind of strange force on the highway which pulls people backwards and forwards, and it's all nonsense. You all know very well you chose a strange coordinate system or a strange reference frame which is accelerating, and because you're in an accelerating reference frame, you're feeling all these inertial forces, which are spurious forces if you want. I mean, you really feel them, right? They're not spurious in that sense, but you don't have to attribute them to some kind of source. All you have to do is step outside from that crazy reference frame into something a little bit more natural to the system you're in, and you'll find that there are no forces. Exactly the same way in gravity. You start coming up with all kinds of theories that there's a gravity force, and that's why things move like this in trajectories. Say it's nonsense. Just step into a more reasonable reference frame, right? Namely free fall, and you'll find everything is very simple. Things move in straight lines. The cannon shoots the thing straight to the hole. You know, why complicate life? Everything is very simple. You're in free fall, you're in inertial motion, your world lines are geodesics. And that's it. What is the true phenomenon? Nevertheless, despite the fact that everything is simple and everything is a geodesic, you do notice that there is some kind of motion towards each other. In other words, there's a geodesic deviation. I'm on a geodesic, you're on a geodesic. Our geodesics are somehow approaching each other. Yes, of course. There's a non-zero curvature. So, obviously, that doesn't destroy the theory, just opposite. It's the explanation. Right? We're both on geodesics, so the geodesics converge or diverge or whatever, depending on what the curvature is. You don't need any gravity force. Gravity doesn't enter here anywhere. There's no such thing. In the wording, I saw this in a book by Eddington. He says that forces, or gravity force in particular, is something that you invent in order to try to maintain some kind of a mindset that you're in a flat space. If you insist that you're in a flat space, it's like the person on a merry-go-round or in the car insisting that they're at rest. So when you insist that you're at rest in that kind of reference frame, right, you have to start inventing all kinds of forces to explain why, if you're in a reference frame at rest, you have all these forces on you. So you invent all kinds of stuff. And the same thing with gravity. Gravity is an invention. If you want to insist that you're in flat space-time, you're going to have to invent this force of gravity that reaches out from the planet Earth or from the sun and pulls you and pushes you and stuff like that. But if all you do is step into a reasonable frame in free fall, you realize that you don't need to invent any of this stuff. There is still a phenomenon, the phenomena of geodesic deviation. Yes, of course, because you're in perfect space.